Thank you very much. Firstly, I'd like to thank the invitation from the Bertarellis to come and present at this conference. My experience in Chagos Archipelago has been from two expeditions in 2015 and 16, where my goal was to try and provide some interpretation of how the physical oceanography was shaping the biological environment. And I should almost apologize at this stage insofar as I'm a physical oceanographer. Most of the time when I talk about the physics of the ocean, people tend to glaze over. But what I'm trying to achieve in this talk is to highlight the dynamics that may be important to the biology. And in particular, what I'd hope to stimulate is a discussion with the biologists as to the extent to which the physics I'm going to talk about today, the internal waves over the seamount where we've heard that silvertips aggregate, are responsible for the aggregation of those sharks. So the motivation for this work really stems from, I would argue, the growing recognition that animals in the marine environment respond to changes in the physical oceanography. And when we talk about physical oceanography, I'm talking about currents, obviously, that most people are familiar with, driven by things like tides and the wind, but also changes in water properties. And by water properties, I mean temperature and salinity are the most basic. And some examples of how we know that animals respond to these changes are, on the left-hand side, basking sharks tracking thermal fronts, in this case off the coast of the UK, with the fairly obvious explanation being that the convergent currents at thermal fronts bring together the plankton on which the basking sharks feed. And they know this, so they know by tracking the fronts, they're able to benefit from that accumulation of plankton. The middle panel corresponds to some work I did with Alice Jones from Southampton, now in Australia, where she'd done a lot of survey work to demonstrate where porpoises foraged over Runnelston Reef near Land's End and when. What we wanted to try and do was understand why. And it was fairly opportunistic. She just did a 12-hour survey with some current meters and CTDs to look at the water properties. And from that, just from 12 hours, we were able to identify that the porpoises forage at a particular place and time over the reef, governed by the release of internal waves that I'll be talking about in a minute. But I might as well point out at this stage, when I say internal waves, it sounds somewhat esoteric, but you can think of internal waves as waves just as you'd see on the beach breaking on the shore, but instead internal waves are within the interior of the ocean, okay? And what I'm going to be talking about is the role of internal waves breaking over a seamount flank. So think of a beach, think of the waves breaking on the beach. In the ocean interior, you get the same kind of process, waves breaking on, instead of a beach, an underwater slope. The difference being in the ocean interior, they're much bigger and much slower. And what I'm going to be talking about is the potential role these internal waves play in shaping, in particular, predator-prey interaction. And the final example I've got on the right-hand side there is some recent suggestions that great whites, for example, prefer warm core eddies in the Gulf Stream. So in Chagos, what I'm interested in trying to understand and explain and contribute to the biology, I guess, is why do we have such dense shark aggregations, specifically over Sands Seamount? I'm really pleased that Barb mentioned that Sands Seamount is, you called it an MPA within an MPA, and I'd call it a hotspot within a hotspot. And I think, from my perspective, that's why I see the importance of this. Obviously, biot itself is a hotspot within the Indian Ocean. When you look at chlorophyll, for example, you can see it's very productive. And we know that it's host to a huge aggregation of biomass and diversity. But even within biot, we obviously have these hotspots. And if we want to develop adequate conservation strategies, we need to understand why these hotspots are indeed hotspots. And so in that case, over Sands, I'm trying to understand why do we have the aggregation of silvertips. But the trick in terms of interpreting it is they're not just over the entire seamount. When we look at, for example, acoustic surveys, and this was from 2016, courtesy of Andy Briley and Roland Proud, and I did see Tom earlier. Tom Letizier, you here? There you go. Can you remember the first discussion we had in the lead up to the 2015 expedition? And we were talking about where to put the mooring, and you showed me that acoustic transect from some very early work. And what was striking about it, what made me very excited in a fairly geeky way, I guess, was that you could see a very, very distinct increase in echo intensity, which means there's stuff in the water over the drop-off. So what we're seeing, what we've always seen, is that the animals that are living over sands are not just randomly distributed over the whole seamount, but they're right over the edges. And for me, it was always frustrating in asking the biologists, well, why are they over the drop-off? And I never seemed to get an answer. And I wanted to understand, is there any physics that could explain why they're over the drop-off? Not over the summit, but over the drop-off. The previous slide showed the movie that we took when we were snorkeling, doing a transect across the seamount. And that just verified what we've seen in the acoustics. When we jumped over the side of the boat to swim with the sharks, we did when we were over the drop-off. When we jumped over the side of the boat in the middle of the seamount, nothing. We could stay in the water for minutes looking for the sharks, and there was nothing. So they really are aggregating over the edges of the seamount. So what I want to understand is what's happening there. And to answer that, the main data I'm going to show you are from 2 moorings that I'll show a little bit more details of in a minute. That in 2015, we put right where Tom and I had identified that increase in echo intensity from earlier surveys over the flanks of sands, where we thought all of this biomass was aggregating. And then just to change things up a little bit, in 2016, I put it right on the summit of Swart, which is the neighboring seamount, almost dynamically identical. And what we see from this CTD transect, and CTD stands for conductivity temperature depth. It's our basic oceanographic equipment for measuring water properties, and you typically profile from the surface to depth to see what the temperature and salinity is. What we see straight away is indications of the effect of the tide on the internal waves. So this was my CTD being lowered down next to the sharks. And we can see 2 transects. The position of the CTD profiles is indicated by the black dots going across the summit of sands. And 2 transects separated by 6 hours. And that's important because the 6 hours is half of a tidal cycle, or half of a semi-diurnal tidal cycle. So you have a complete tidal cycle over 12.5 hours approximately, so 6 hours is effectively your flood, 6 hours later is your ebb. So these 2 transects were conducted half a tidal cycle apart, and what I want to draw your attention to is this blue, cold water on either side of the Seamount summit, and we can see it's markedly different 6 hours apart. Transect 1, we've got this cold water depressed down on the left-hand side, the west side of the Seamount. And 6 hours later, that cold water is now spilling up over the seamount. So this is our first indication that something dynamically is happening. And basically, it's this sloshing of the water up and over the summit. And so the first thing that's happening is that we're flushing the Seamount summit with cold water every tide. Now that's important because what it does is suggest the importance of a well-documented example, the mechanism which is generally always invoked as explaining why seamounts are so productive and was also in a blue planet. And it's, unfortunately, from my perspective, fundamentally wrong. There's never really the evidence for what are called Taylor columns. And Taylor columns basically involve the upwelling of nutrients to the sunlit upper ocean above seamounts. And because of the rotation of the Earth, effectively, you form what are called Taylor columns, which are basically giant whirlpools on top of seamounts that retain those nutrients, which then stimulate primary production, so your marine algae, which then draws in the zooplankton, which are then eaten by the fish, and so on up to the top predators. That's the kind of classical view of why seamounts are important. And that may be somewhat true on very large seamounts, but it's definitely not the case here in biot, because in biot, the seamounts are too small, they're too narrow and too steep. And we can see from this left-hand panel that if you release your nutrients here at time 0, 4 days later, when you measure how far the currents would have taken them, they're 150 kilometers away. So if those nutrients being upwelled in that cold water up onto the seamount summit are indeed promoting primary production and stimulating the ecosystem that way, they're not doing it over the seamount. So something else is happening over the seamount to eventually cause the aggregation of these sharks. And just to point out this figure, this shows the nitrate in that cold water being upwelled onto the seamount summit. So we've got our nitrate concentration on the y-axis, and the color corresponds to the temperature. So we can see over time, we get these events driven by the tide, sometimes more pronounced than others, where we're getting cold, nutrient-rich water being upwelled onto the summit. But the key point is those nutrients are not staying over that seamount to promote primary production that then sustains the zooplankton, that then sustains the fish, that are then eaten by the sharks. Those nutrients are washed a long way downstream. So something else is happening. So to understand what that is, we're going to focus on the moorings that were in the first instance deployed over the flank of sands, and then secondly over the summit of Schwartz. And these are our moorings, big heavy-duty kit, scratch the boat, cut your hands. We've got our anchor at the bottom. These are taut subsurface moorings. So we have a big anchor at the bottom. We're very pleased that we recovered that anchor at the end of 2016 with an anchor recovery system. Not particularly safely, it must be said, but we did it. And then along this mooring, we have a series of temperature sensors measuring the temperature. We've got our current meters in the middle, one upward looking, one downward looking, and these are acoustic Doppler current profilers, which combined with our temperature sensors provide us full water column measurements of velocity and temperature at about 2-meter vertical intervals over the entire water column. And in addition to that, we've got our instrument frame, which I showed you the results for the nutrients in the previous slide at 8 meters above the bottom, that we're measuring the nutrients, but also particles, and I'm going to show you a picture from the particles later on. And then this mooring is held taut by this buoyancy at the top. So the whole thing is underwater and sits there in the water column, measuring the change in velocity, but temperature over the 2-week deployment. And when we look at the results from the temperature, we can see a couple of really important points. Firstly, this is the whole time series from 2015. And we can see our isotherms, which are the lines of constant temperature, moving up and down at the position of the mooring by 20, 30 meters every tide. Starts off being dominated by the semi-diurnal tide, 12-hour period. Later in the deployment period, it becomes mostly a diurnal tide. And we can see that in our temperature variance spectra. And this shows us how energetic motions are as a function of their frequency. Okay, so we can see we've got our diurnal tide. We've got our semi-diurnal tide at 1 cycle per day, 2 cycles per day. They're the most energetic. But what we can also see is this, at 20 meters above the seabed, the red line, we can see, rather than a straight line going down, becoming less energetic with higher frequencies. We've got this kind of broad band increase, and that are these waves. These are much higher frequency waves, not tidal. These have a period of the order of 4 to 5 minutes, which is slow because they're internal waves, but look how big they are. And I was looking around trying to think how big this room is. These are 10 to 20 meters amplitude. So, you think of surfing in 20 meters, you wouldn't do it unless you're nuts. But these are waves of about the size of this building, constantly pushing by the flank of sand seamount associated with these tidal perturbations. And what's happening are lee waves. And this is a movie that I need to click again, I think, to start. And I didn't want it to start because I want to explain what you're going to see first. This is what's happening. And I must say, I've got this all written up in a paper, which I'm waiting the reviews for. I've never been so certain of any interpretation of observations as I've been in this case, because everything matches up perfectly. This is a simulation by a former colleague of mine, Martin Bausman, for Hawaii. And what it shows is the formation of a leeway and its eventual rebound as an internal bore. What you're going to see, this top panel is the current speed, and you're going to see the coloring become red as the current flies over the top of the summit down. And you're going to see the black lines, which are your isotherms, your temperature, become depressed. And then this line, which shows you the current increasing in intensity to the right, will weaken, it'll reverse, and you'll see the rebound of those isopycnals up over the summit. So if I now run that movie, which I trust is what's going to happen, current intensifies, pushes the isotherms down, it's strongly turbulent. This red shading means turbulence. Current reverses, and the wave rebounds up onto the summit. And that's what's causing our flushing with cold water. And this is the evidence from the mooring. I only want to draw attention to a couple of key points and basically evidence for what we've seen in the movie. This is our temperature. And we can see every tide, we've got this cold water flushing through the bottom of the mooring. That's the blue shading. And corresponding with that are this yellow shading in the cross-slope velocity. And that's the component of the velocity going up the slope. And so this is that cold water being pushed straight up the slope onto the summit of the seamount. So turbulent, energetic events, and most importantly, they're concentrated right at that drop-off. And they're persistent, they're happening every tide. What happens to them as they then reach the summit? And that's the final part, and this is from the mooring over the summit of Schwartz the following year. So these are the stages of evolution. I've made up a little cartoon of showing what happens with a lee wave. The current is directed to the west, it depresses the isotherms, they steepen, the current then reverses, or weakens and then reverses, and that wave rebounds up onto the summit, flushing the summit with cold water. And that's exactly what this is showing now from the mooring over the summit of Schwartz the following year. We can see the cold water rushing over the summit of Schwartz, again, 20 meters high. So imagine you're sitting here now on the summit of Schwartz, and you get a 20-meter mountain of cold water flushing over the top of you, rich in nutrients. It's very strongly sheared, which means that the horizontal velocity within the cold water flushing event itself is moving in a completely different direction to the water above it. You can see it's moving in the northeast direction, whereas the water above it is moving west. So this cold water is moving in this direction, the water above it is moving completely opposite directions. The importance of that is that the shear, which is the vertical gradient in the horizontal velocity, generates turbulence. And turbulence is really important for things like predator-prey interaction. It perturbs the way that fish swim, for example, and makes them more visible to predators. You've got these short period waves riding on the back of this cold water flushing event. And that's important because these nonlinear waves generate strong vertical velocities. Water doesn't like to move vertically in the ocean, and it needs something special to happen to generate strong vertical velocities. And the primary candidate for that are these nonlinear internal waves. And the reason they're important is because as these waves move along the seabed with strong vertical velocities, they're resuspending all of that material at the seabed, providing food for filter feeders and the fish that feed on the resuspended particles. And finally, and this is the last little piece of the puzzle, we can see strong echo intensity from our current meters near the bed, only during daytime, which is kind of odd. I mean, I looked at that and thought, well, surely it can't just be during daytime. But it is, and it's trapped right at the bottom. And if this was a lecture, I'd be asking for answers from the audience. But it's zooplankton. It's zooplankton that are trapped over the Seamounts summit during daytime, because zooplankton, during the daytime, like to hang out in the deep scattering layer where they're safe from predation because it's dark. And then when the sun goes down, they come up to the surface to eat all the phytoplankton. The problem they've got is when they're over a summit and the sun comes up, they try to go down to the deep scattering layer at 400 or 500 meters, but they're stuck over the summit of sands. So you have a nice dense layer of zooplankton trapped over the summit of the seamount. And that's what we can see in our holocam that was moored at 8 meters above the bed. During nighttime, when they're all at the surface, we don't really see any zooplankton. In the daytime, we see a much greater abundance of zooplankton. So we've got a couple of things happening. We're getting zooplankton being trapped over the summit during daytime. Those then sustain the fish. And then we've got these really energetic, dynamic internal wave events, which are just stirring everything up, increasing predator-prey interaction, and so forth. And so the unanswered questions and what we'd like to be doing in the future, subject to funding, of course, is how do the internal waves shape predator-prey interaction? Because that's what the hypothesis is. We've got these energetic events that perturb the way in which the sharks interact with the fish. And there's a huge wealth of literature that I did touch on and then got rid of it because it would be a lecture in itself. And I'm sure there's many biologists in the audience who would have a lot to say on the way in which turbulent flow perturbs the way that fish, for example, school. And this is work by one of my colleagues at Plymouth who showed this is an acoustic transect. We can see the internal waves. Fish school in the internal waves. They respond to those perturbations in the physical environment. And my suggestion to the biologist is that these internal waves are causing the fish to school over the flanks of the seamount. And for the sharks, it's like shooting a fish in a barrel. They just charge in with their mouths open. For the individual fish, they think they're avoiding predation. But for the sharks, they just see a big cloud of fish in front of them. The fish are schooling because of the impact of those internal waves. But we need to look much more closely in the future to the timescales match, when the internal waves are there and the fish are schooling. Pete, I saw earlier, Pete Carr, there you are. So when we were doing the CTD transect over sands, we noticed that there were seabirds foraging in discrete patches around the edge of the seamount. Well, these internal waves that I've been talking about, they generate rays of energy that move diagonally away from the seamount flanks, upwards and downwards. And so you're getting turbulent flow at the surface as well. And I wonder whether that's a dominant mechanism in determining these patches of increased foraging activity by seabirds. I think you need to run this from up top, I think. It's really dangerous to be looking at biot in a microcosm, and in particular at seamounts, in isolation and thinking that whatever's happening there is due only to what's happening right there. You need to pull back a little bit. And in particular in biot, the whole region is subject to a range of processes that many people in the room will be familiar with. Well-known ones are the Indian Ocean dipole, the monsoon. More esoteric processes are things like the Madden-Julian oscillation. But these are basin-scale processes that influence, amongst other things, the Seychelles-Chagos thermocline ridge, which is a ridge of cold water that extends up towards the sea surface, bringing with it nutrients that then stimulate primary production and strongly impacts on the tuna. If we don't understand what's driving these processes, then we can strongly misunderstand and misinterpret what's happening in biot when going there for a day or so. And then finally, these internal waves are ubiquitous. They're everywhere and active at all times. As well as influencing predator-prey interaction, they're almost inevitable. They definitely impact on coral. And I must say I'm finding it frustrating almost in that I keep seeing this literature, high-level literature, invoking temperature fluctuations for releasing the stress, thermal stress on surface corals. I mean, it's internal waves. People don't seem to be mentioning the internal waves, I guess because they're seeing it from a biological perspective. But I wish they'd come and speak to me, because this is simple from a physics perspective. These are the internal waves flushing the slope with cold water, drawing cold water up the slope, relieving the stress on the surface corals, but potentially transporting larvae and allowing those surface corals to recover. Thank you.